This is a recording of the talk before giving the talk, so because the actual conference WADT will not be recorded, hence I just give it for archival purposes. Right, thank you for the introduction. So let me start with a claim you hopefully find not overly bold, namely that formalizations are useful, both in algebraic specification languages, that's probably why we are here, right? And deduction systems. So then if you find formalizations useful, you will quickly notice that theory graphs rise unexpectedly, because to prove even the simplest theorem in any mathematical subfield you like, you really need to formalize the whole dependency closure. Right, and probably in the last decade, we've made the greatest achievements of proving the Kepler conjecture, Fay-Thompson, and the four-color theorem, showing off the capabilities of formalizations and deduction systems. Right, and as known from software engineering, the larger your code base gets, the more modularity becomes essential at those large scales. In principle, for two reasons. Reason number one is for human maintenance. So the less redundant the code is, the better a human can grasp it. And for reason number two, that the more modularity we have, the more structure we have, the easier it becomes to run automated tools on it for indexing, retrieval, cataloging, for bookkeeping, and whatnot. So that also determines our research program of finding ways to achieve modularity at large scales. Right, and again, we might compare it with software engineering, where to achieve modularity, we basically have two options. So option number one is use something built into the language. So use object-oriented programming, use some design patterns. For us, that would probably mean use theories, use theory morphisms. And option number two, to somehow evade the language and go meta. So meta programming also achieves modularity. And that's what we're after here. And we do meta programming with diagram operators. So we operate on diagrams of formalizations. So for an introductory example, consider these diagrams. So on the left, we got a diagram of formalization for some part of the algebraic hierarchy, starting with magma, monoid, going over to group, and much more. And consider that we formalize all of them in a multiplicative fashion, meaning that, oh well, we denote the binary operation of a group by c dot, the inverses by power to the -1, and I don't know, repeated binary operations by exponentiation, right? And now we would like, of course, to use groups as well in an additive setting. Say somewhere down the line in a theory, we would like to say, oh well, let's import the formalization of additive groups. To mean, let's import the notation for plus, for multiplication, and for minus signs instead of the notations I mentioned before. And right, but how do we do this? So in a pen and paper setting, that's very easy. So you might find in an undergraduate textbook, just at most one paragraph perhaps, saying, oh well, if we got structure A, then we define the convention of talking about additive A by meaning blah, blah, blah. So that's actually one kind of meta programming. And why not mimic this? So why not just declare that diagram we have on the left is some magma hierarchy diagram. So really fill it into a variable and then make it additive with one, and really one invocation, only one invocation of a diagram operator. Right. So having brought up that example, let's consider the spectrum of operators and how this talk fits into there. So at first, you can start with fixed theory operators, considering inclusions, co-limits such as unions, translation along single theory morphism, and so on. Right, many languages have them. Then you can go over and consider diagrams to be part of the object language somehow. For example, DOL, the DOL language allows to form named diagrams, and also, for example, to build unions, to remove things of a diagram or of a network, how they call it. Right. And then the second author, being my advisor, Florian Rabe, and together with Yasmin Sherode, extended that to diagram operators. Also in a user programmable fashion. So diagram operators now just are coded functions accepting a diagram as some abstract syntax tree and outputting another one. So it's some are coded into the system, but notably it's user programmable in the following sense. So they use the MMT system, which is a formal system where you can formalize things, which is very minimalistic and foundation independent actually. And in archives of formalization, so you can of course have your formalization files, but you can also package Scala code. So you can package as part of your formalization archive actually diagram operators. So if you decide to formalize some specific subfield, which is your favorite, right? And then you see the need for a very specific diagram operator for doing something no generic operator could ever do, right? So there's no chance that anyone would implement it in the core system. You are free to implement that operator as part of your archive and redistribute it as part of your archive. So that also fits in our general research program of achieving modularity. Right, and in this talk, we're gonna classify abstract properties of such diagram operators to overall ease specification and implementation. Sorry. Right. So consider the example that the diagram operator is actually very boring on diagrams or theories because its actual action is just on theory declaration. So it just works on a declaration by declaration basis. And its whole action of theories, morphisms, and diagrams is just a borrowing homomorphic extension. So in that way, we really want to specify it only in declarations and only implement them on declarations. So that's what we're after. Right, so that sets the setting for this talk. And in the following, I will shortly introduce some syntax and semantics for our purposes, and then basically provide a rundown of some abstract properties we studied with a running example, and conclude the talk with some more examples and some short visual case studies. Right, so let's begin. So we also work with the MMT system and more precisely with the Omdoc MMT language, which we see on the left. So we got diagrams consisting of theories and views, where theories are named, effectively named lists of declarations, and declarations are constant declarations over some dependently typed variant of lambda calculus. So we can encode a pretty wide range of things, like we can encode theorems, proofs, inference rules, judgments, definitions, and so on. And then we got views, also named views as lists of assignments relating to theories in the hopefully well-known sense. Right. So to give semantics to this syntax is pretty easy actually. So we just come up with a category phi, where the objects are just now unnamed theories. So we call them flat theories and unnamed morphisms. So that actually is a nice categorical structure. But so far that would be boring, of course, because the syntax nobody would use that syntax in real life because we cannot structure theories. Hence, let's add one simple modularity feature for our purposes, namely inclusions. So we can include some other named theories, and now the semantics interpretation from syntax to semantics actually gets interesting and is denoted by flattening. Right. So that's another take on what if a diagram operator actually doesn't care about inclusions. So we should be able to specify and implement it just on the semantic side, right? And depending on its abstract properties, just lift it to the syntax with inclusions. Or in general, lift it to a syntax with more modularity features. So in this talk, for simplicity, we restrict ourselves to inclusions, but in general, the concepts may apply further down the line with more modularity features, which can be seen in real life systems, right? Good. So that's the syntax and semantics. So let's define what we mean by operators. So a syntactic diagram operator is just a partial function as before from the set of diagrams to the set of diagrams. And now a flat diagram operator is a partial functor from phi to phi, whereby partialness, I mean being defined on a subcategory, right? So for example, we can take the subcategory for a fixed theory T, namely the subcategory of T extensions. So by that, I mean the subcategory consisting of all the theories containing copies of T. Because recall, if we just work on the semantic side, we don't have inclusion, so we have to work with a notion of copies. Right. So let's present the running example we are going to use. So we're going to use the Pushout operator in phi. So let's fix a morphism L from S to T. Then we can push S extensions to T extensions. Right. And from a practical point of view, this is really nice because computing the Pushout of phi amounts to translation. And we often want translation. Say we formalized a theory as on the top left in the image, which is a very basic meta theory, perhaps a logic theory, right? And we formalized a bunch of theories, a whole diagram below it. And then we came up with another theory T, which is also pretty basic, and then we related S to T via M, so saying, implying that we can translate S expressions via M to T expressions. Then naturally, we should also be able to translate everything built upon S to something built upon T. So that's what the Pushout just does. That's just the Pushout. So that's why it has practical significance. Right, so let's consider the Pushout operator in more detail. So what does it do on declarations actually? So again, we have S and T, and then now let's apply it on a theory A consisting of constant Ci. Right, and the Pushout is computed as follows. So because we are in a flat world, we first take everything of T, the codomain of the morphism over which we are pushing out. And then basically for every constant, which is really an A, and not just copied from S, we just translate its type and definitions component via M or via some homomorphic extension of M. Right, so here we can already see PM somehow works declaration-wise. So that's an abstract property we are going to name sublinearity later on. Right. But before, let's first consider what this operator is supposed to do on syntactic diagrams. So let's have a look into the future, what we actually want it to do. So now consider this actually syntactic formalization of in an indeterminate element type and the theory of lists and trees over that, and theory of search trees, whatever it might be. And then we witnessed by this morphism M that the natural numbers actually give rise to an indeterminate element type. So we can, or we should be able to just push everything over to get the list of natural numbers now, to get the theory of trees over natural numbers, and so on. And notably, the translation of search tree, right, makes use of the translation of trees. So we don't flatten inclusions, but actually what we intended to do is recurse for inclusions. So if an inclusion occurs, it should recurse into translation to be include preserving. Right. So let's collect all the properties. They were not that many, but let's have a broader look on them. So again, our goal was to identify useful properties, to somehow specify and implement operators in the simple flat world, and lift them. And hopefully lift them in a semantics preserving way. Right, and we know PM was functorial. I hope you believe me. Sublinear and include preserving, two notions I'll present now. And also, actually, it's homogeneous, which is the notion I won't present here. Right. So we noted PM works declaration by declaration, and that we capture by sublinearity. So we call delta sublinear. There's a partial variant of delta, the binary delta, such that if we apply delta on a theory sigma with additionally one new declaration, well, then it's just the action on sigma plus some action on the declaration, which might depend on the sigma. So we allow some context aware action. And then we can prove sublinear operators actually uniquely determine the context aware action, which should actually be true if the notion is correct. And sublinear operators are uniquely determined by the action on the empty set and the context aware action. So if we have the action on the empty set of a theory, then we can slowly walk our way up to the whole theory just by following the context aware action step by step. Right. And that eases very much the specification of PM. So that's much more concise, right? So what's the practical significance now? Specification we ease, okay, that's fine. But in the implementation, which we want after all someday, because we actually want formalization in a real world computer, we now have to just provide run method effectively, which is nice. Right. So that concludes sublinearity. So let's consider the other notion of include preservation. So we call an operator include preserving if it's monotone on the subset relation on flat theories. So this makes sense because the subset relation of flat theories is actually morally the include relation. Right, NPM is include preserving. And this is no surprise because sublinearity and include preservation are equivalent. So we can just take a sublinear, right, and the significance for the implementation or rather, let's say, include preservation does not help us with specifying an operator. And neither does it help us to implement run because it's very abstract. It doesn't say what the operator actually does, but sublinearity does. So let's take a sublinear specification implementation, and then we know it's include preserving, and then we can actually make the implementation lift it to the syntax with inclusions. So that's the takeaway. Include preservation allows us to lift, while sublinearity allows us to easily specify and implement. And now we can use that to climax in our main theorem that lifting preserves semantics. So let delta be a sublinear operator. Then we can define as lifting delta hat I'd say morally the obvious way, but notationally it's a bit cumbersome. So if a theory occurs including theories S1 to Sn, then we recurse into S1 to Sn and apply the sublinear operator on the flat parts. So we can extend that for views and diagrams, of course. And now our theorem says that if I apply first the lifting, and then take the semantics, that's the same as taking first the semantics and then applying our actual specified implemented operator. So in specification and implementation, we give away a definition of delta, then the implementation under the hood lifts it to delta hat and just applies delta hat. Note that include preservation is also crucial for efficient diagram operators, right? If we have two theories sharing a lot of common theories and I apply a diagram operator on both, then I can just cache the results on all the previous diagrams they're built on and just have to apply the remaining context and reaction on both theories individually. So we really want caching in implementations. Right, so far so good. So that concludes actually the running example with a rundown of two properties we studied. Let's consider some more examples and add some quantitative numbers for case studies. Right, so another operator we came up with is the Church-Perry operator. So for those who don't know Church and Curry type theories, let me tell you, so there are generally two flavors of type theory, Church and Curry. So let's, as an example, let's just formalize the type theory for product types. So in the Church flavored variant, which you can see on the top, there we got first a type constructor, right? Taking two types and outputting another type, which is our product type. And then we got a term constructor, which is typed. So that's characteristic of a Church flavor, that the term constructor is typed. So it takes two types and then two terms of exactly those types and then outputs a term of the product type. Instead, we could also follow the Curry variant, having again a type constructor and then an untyped term constructor. Right, I hope you can see that. And then, of course, additionally, because as an implication, we can then construct the pair of everything, right? Because, and then of course we need morally something additionally to ensure well-typedness somehow. So we got the necessity of a typing rule, which is depicted in the third line here. So it takes two types, two terms, two untyped terms, and then two typing judgments, namely if A is of type A and B is of type B, then the typing rule actually gives us the judgment, oh well, the pair is also of type A times B. Right. And then we applied that operator in Latin too, which is an MMT archive of ARAS, I'd say. So it's a very modular archive. So it features many hundreds of theories and built up in a very modular way for fundamental things like type theories, logic, arithmetic, basics of mathematics, I think vector space a bit, and so on. And there we had 100 lines for Church and Carey, manual kept in sync. In fact, Carey was out of sync. So you see that with lack of modularity, inconsistency might creep in. So now the red part actually is the Carey run, and we can fully replace it by one line of operator invocation of Church Carey. Now, the reduction of 60 lines is actually not too important. I'd say 60 lines aren't that much, but the much more important key takeaway is that now we have consistent knowledge now and forever. Because no one can fiddle with the formalization of Carey anymore because it's somehow hidden in the operator invocation line. Right. So as another example, we got typified full, where where we start in the first order logic world, and there we consider the actual formalization of first order logic. So we have to so we consider the formalization of the for all symbol, for the existential symbol, and for the natural deduction rules. And actually it turns out, of course, we can do everything pretty much the same, morally speaking, in the sorted first order logic world too, but just with types added into the appropriate places. So for all, it was previously TM to prop. Now, for all in S-full is abstracted over one type, over one sort, A, colon to P, and then it's TMA to prop. And we can do this consistently for all existential, for all introduction, for all elimination, and so on. And that brought us to typify full in Latin too. And now we can also eliminate the red part, which, by the way, was now really in sync, manually kept in sync. So again, we had a reduction in lines of code. Right. And then we got some more examples, which we won't study, which we won't present in this talk for time reasons. So we can compose diagram operators. We can union diagrams as and all. In the universal algebra world, we can build up the theory of homomorphisms. So given a theory, say of monoids, we can automatically build the theory of homomorphisms of our monoids. Same for substructures, coefficients, products. Switching between additive, multiplicative notation. In logic, we had Church-Carey as presented, typify full, polymorphify, which also does some full fiddling, and cryptify, which also somehow abstracts declaration over some world type. Right, and I think so these are pretty much very generic examples, and I'm sure there in every mathematics subfield there might be the need for specialized operators. And now we have the beginning of a modular way to specify and implement them. So hopefully that paves the way for more specialized operators appearing. Right, so let's conclude the talk. So we understood that we can achieve modularity by method programming, and we can achieve method programming by diagram operators in the formalization world, which actually lessens redundancy, which is never good for human maintenance, as we've seen, to increase consistency. Right, classifying diagram operators, identifying abstract properties which are useful, easy specification and implementation, and pen and paper theorems such as the semantics preservation of liftings ensure that we can appropriately and efficiently deal with diagram operators given in a concise way. Right, so thank you for listening. And if you have any question, don't hesitate to drop an email or to drop by. So bye everyone.